Hello friends, I am Sumant Kumar and you are watching Diagonalize. Right, today we are going to explain a very important topic, that is diagonalization of a matrix. Right, so in this session we will discuss about 3-4 points. First thing, what is diagonalization? That means what we mean actually by this diagonalization process. Correct. Second thing, we will we will discuss, are every matrices are diagonalizable? If every matrices are not diagonalizable, then what are the condition we should impose, right? Or what are the factors which will affect the diagonalization? That means which matrices are diagonalizable. Second thing, right? And then we will discuss what is the process to diagonalize a matrix, right? If a matrix is diagonalizable, right, then how can we diagonalize it? What is the process? That we will discuss it, right? And next we will find the reason to diagonalize a matrix. What are the reason actually for that we diagonalize a matrix, right? That means you can say the application of diagonalization, right? And this is also very interesting, right? We will see how this diagonalization process is important and play an important role for some application, right? And at last we will some we will solve some MCQ, right? Objective question we will try to solve, that depends on this diagonalization process, right? So this is our plan for this session, right? So let me start with what is the diagonalization. Correct. So what is the diagonalization? Basically, when we call diagonalization, right, that means you can say a square matrix, right? Here it is automatically, you can understand, we are diagonalizing a matrix that is a square matrix, right? So a square matrix is said to be, correct, you may called a square matrix. A square matrix is said to be diagonalizable, correct, is said to be diagonalizable when is said to be diagonalizable, correct, diagonalizable if if a is similar to a is similar to D, correct? You can say similar to DA, right? And DA is what? D is a diagonal equivalent of A, right? You may call this is a diagonal matrix. That means simply you may call that this diagonalization is a process when a matrix can be represented as a diagonal equivalent, right? You may called A is similar to D, correct, diagonal equivalent corresponding to matrix A. But question is, what is the similar? When a matrix, when two matrices are said to be similar, right? How we define it, right? So let us define first similar matrices, right? So that is, for it there exists a matrix, right? That is, you can say A is equal to, right, P into DA into P inverse, right, where where P is an invertible matrix. Correct? P is an invertible matrix. What you say, right? A matrix A is said to be diagonal, right? Diagonalizable, you may call, right? Diagonalizable if there exists a matrix P which is invertible such that A is equal to this one, right? If this identity holds, then you can call A is diagonalizable matrix, right? So actually, what are the benefit of this diagonalization? Right? We will discuss it later. But I am here giving you a property of what you say similar matrices, right? That means property of similar matrices say that the characteristic polynomial, you can say the characteristic polynomial of both matrices, right? Characteristics polynomial of A and DA. These are the two equivalent matrices A and D of A and D are same. And so you can call these have the same eigenvalues, right? With multiplicity. With multiplicity means that if A has eigenvalues 2, right, and it is repeated twice, then it means DA, that is this diagonal matrix, have the same eigenvalues and repeated 2 times also. This is the meaning of this property, right? So easily you can simply say that this A and DA are equivalent, then have same characteristic, right? This is the benefit of diagonalization, right? Now question is what? Next question is that which matrices are diagonalizable, right? I mean to say, is every matrix is every matrix diagonalizable? No, not every matrix is diagonalizable, right? Let us take one example, right? If I am taking this matrix, right? Suppose 0, 2, 0, 0. This is also a matrix, but this is not diagonalizable, right? This is not diagonal matrix, or you can say not diagonalizable as well. So every matrix is not diagonalizable. So question is what? Which matrices are diagonalizable? What are the condition you may impose on the matrix so that you can say this is the necessary and sufficient condition for the existence of this diagonalization, right? So for it, right, you can take this note, right? That means diagonalization of a matrix basically depends on the eigenvector, correct? This is basically depends on the eigenvector, right? So you can say that a matrix is diagonalizable. You can say that n by n matrix, right? N by n matrix is diagonalizable, right? Is diagonalizable if and only if, right? If and only if it has, I mean to say this matrix, a n by n matrix A is diagonalizable if and only if it has an independent eigenvector, n independent eigenvectors, then you can say this matrix is diagonalizable, right? This means if order of this square matrix is n, then you have n independent vector, then you can say the matrix will be diagonalizable. This is the only condition, right? And all the rest condition will depends on this statement, right? So one another statement you may write, right? Or another way, right, you can say that if a matrix, if A has n distinct eigenvalues, these are the important theorem you may directly use to verify, to check whether the given matrix is diagonalizable or not, right? If A has n distinct eigenvalues, right, eigenvalues, then A will be diagonalizable, will be diagonalizable. Why? Because there is a theorem which says that if A has n distinct eigenvalues, then corresponding eigenvector will be linearly independent. And so this statement is also connected to the previous one. And that's why I'm telling you this is the important statement, right? And which specify, or which you can say which is the necessary and sufficient condition for the diagonalization, right? But you may find another result which maybe depends on this one, right? So this is also important. You can use this result to find, to check whether a matrix is diagonalizable or not diagonalizable, right? For example, let us take one example, right? Suppose I am giving you a matrix, right? Just see, I'm taking 2 by 2 matrix. Suppose this is 2, 3, 0, and -1. Correct? So from the matrix, it is very clear that this is a triangular matrix. You say this is a triangular matrix, correct? And you can easily find the eigenvalues, yes or no? So eigenvalues corresponding to this matrix is 2 and 1. As we know that diagonal element of a triangular matrix will be eigenvalues, right? So clearly these two eigenvalues are what? Distinct, correct? These two eigenvalues are distinct. So using the above result, you can say that, right, this implies that this matrix A, you may call this matrix A is diagonalizable, right? So this is the way to check whether the matrix is diagonalizable or not diagonalizable. But sometime your what do you say, suppose I'm taking one more example of 3 by 3 matrix, right? Suppose this is a matrix B, and here we are finding 1 0 2 0 1 3 0 0 2. So again I am taking the triangular matrix. So clearly the eigenvalues are what? 1 comma 1 comma 2. So here this eigenvalues, that means 1 repeated 2 times. So double roots are finding corresponding to 1, right? So here may or may not, you cannot say using this result that this will be diagonalizable. So may or may not be diagonalizable. But this time, what will you check? You will check whether corresponding to 1 you are getting 1 eigenvector or 2 eigenvector, right? That means, is there any shortage of eigenvector? Is there any shortage of eigenvector? Right? If shortage is there, that means corresponding to 3 eigenvector values, you are getting less eigenvector. That means only 2 eigenvector you are getting. Then there is a shortage of eigenvector, and that time you can say this matrix is not diagonalizable, right? So this is another way to check, but this is the important. Always you will check whether the corresponding to n eigenvalues you are getting an eigenvector or not. So this is the way to check whether a matrix is diagonalizable or not diagonalizable, right? So now let me define, right? Now the question is, how will you find the diagonal matrix? This is the important thing, right? So now let me define the diagonalization process, right? So let we say, let lambda 1, I am considering a n by n matrix, right? So let lambda 1, lambda 2, dot 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 lambda n are eigenvalues, right? Eigenvalues, I am denoting it by lambda s, right? Eigenvalues. And v1, right, v2 and dot 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 vn are the corresponding, what you say, eigenvector, right? Corresponding eigenvectors, right? Then right, then your what you say, then there exists a matrix P, right? You can say then there exists a matrix P. This is invertible, right? Invertible matrix will exist, right? Invertible such that A, correct, A is equal to, or you may use the concept of that. So A is equal to P dA, that is diagonal equivalent of A, correct? So corresponding to this matrix A, P inverse, such that A is equal to P into D into P inverse, right? Where how will you construct this matrix P? P is just a matrix, right? Is a matrix whose column is nothing but the corresponding eigenvector, right? Whose column are nothing but corresponding eigenvector, right? So I hope you can understand what I am doing here, right? I am taking this eigenvector and keep this eigenvector at first column, right? And dA is a diagonal matrix whose diagonal elements are, right? This is a diagonal matrix whose diagonal elements are nothing but eigenvalues, corresponding eigenvalues, right? So this is very important result we directly use to find the diagonal equivalent of this matrix, right? So this is nothing but what diagonal, whose diagonal element are only the corresponding eigenvalues, right? So here one thing you may remember, right? That means if you are writing vector v1 that is corresponding to lambda 1, then first element must be lambda 1, right? So this order is important, right? And really it will count, right? You cannot change the order, right? If you are writing lambda 1, lambda 2, lambda n, then corresponding vector will be first column, second column, and third column, right? So this is the way to find the column matrix P, right? And this matrix will be definitely what you say invertible, and we called it model matrix, right? We called it model matrix. So finally, what we do, we will find the eigenvalues and corresponding eigenvector, and we will write the vector in the column and to form a matrix, and that the matrix will serve as a model matrix, and that will diagonalize the matrix, right? So our purpose is to find this matrix only. So purpose is what? To find eigenvector only, right? So if you are able to find the eigenvector, definitely you will get the diagonal equivalent of that matrix, right? So this is the way to find the diagonal matrix, right? Now see, you can write this A is equal to P into D A into P inverse, right? You can write it in another form in this way, right? You can change the two matrix by pre and post multiplication of P. So this will be just dA. Suppose sometime you need to find the diagonal form, right? Then this will be nothing but P inverse into A P, right? So these both expression is important, right? Finding while using these two results, you can prove many results, right? Many results, right? So simply you can say the property and characteristic of these two matrices A and DA must be similar, right? So now let me tell you that what is the application of this matrix, right? This diagonalization process, right? Why we need it, correct? Why we need it, right? That means when we find A is equal to, right? When we find A is equal to P into D A into P inverse, right? How can we use it, right? So suppose we want to find the power of a matrix, right? Of a matrix, how we will use it, right? What is the benefit of this diagonalization process, right? Suppose we want to find A raised to the power n. Simply when you are using the multiplication, you have to multiply it n times. A square, AQ, and so on n times. But if you are using this definition, that is diagonalization process, simply you need to multiply maximum 3 times, right? So how we see here, right? So let us find a square. See, a square means this a into a two times, right? It means what? P into dA into P inverse. And again you will write this form. So P into dA and into P inverse, right? Now you will multiply these two, correct? So when you multiply these two, you will get identity matrix, because P into P inverse, this will get identity, right? And when identity matrix is multiplied with any other matrix, suppose in this case dA, you will get dA itself, right? So using these two concept, you can easily find P into dA. Here here what will happen? dA and dA, this will multiply two times, so dA square will come, and now here P inverse. So see, when you are finding a square, simply here d square is coming and no change at P and P inverse, right? This is the beauty of this diagonalization process, right? So similarly, if you want to find a raised to the power 3, correct? Then what will happen? You will multiply it 3 times and you will get P dA P inverse, right? You will write one time, again you will write PDA, that form, that is the similar matrices, right? You can say the diagonalization process we have defined already. We will write it 3 times and we will multiply these two, get identity matrix and cancel out, you can say. So automatically 3 times DA will multiply, right? One time, 2 time, and here one time, 3 times. So d raised to the power 3 is coming, and P inverse, right? So when you want to find the power of the matrix, you will simply shift this power to this diagonal matrix, right? So in general, you may write, in general, you may write what? A raised to the power n is equal to what? P into d A raised to the power n and P inverse, right? This is the method, and this is the way to calculate the power of the matrix. Now see, these two, you simply, you can say that what? An is equivalent to dn, d raised to the power n. It means if this matrix has eigenvalues lambda n, then this diagonal equivalent have the same eigenvalues, both have the similar characteristic, right? So this is the way. Suppose sometime you may ask, right? This a lambda is eigenvalues, right? Lambda is an eigenvalues of this matrix, right? A, right? Then what will be the eigenvalues of A raised to the power n, right? Suppose sometime it will be given just like, for example, right? I'm asking you, suppose a matrix A and has diagonal equivalent. This is given by 1 0 0 0 2 0 0 0 5. Suppose this is the diagonal equivalent of this matrix, right? I am asking you, right, what are the eigenvalues eigenvalues of A raised to the power 2, right? So clearly from this matrix you can say that eigenvalues of A are 1, 2, 3, right? So clearly you can say that clearly 1, 2 and 5 are eigenvalues of A. Then what will be the eigenvalues of A square? Right? A square, it means what? D square. You need to find the A square first. So definitely D square will come here. So here if you square it, then you will get the equivalent. A square is equivalent to this D square. So definitely you can say 1, 4 and 9 are the eigenvalues of A square. So this is the benefit of this power of the matrix, right? Now you can also find the what you say, you can also find the exponential of the matrix, right? So let us find the exponential of A. Second application, correct? I am explaining you the second application, that how will you find e raised to the power A, right? That is exponential of a matrix, right? So see, you can use the same characteristic, right? Same diagonalization process to find the exponential of matrix, right? Let us first write the e raised to the power x, right? This is what 1 plus x plus x square by factorial 2 plus x raised to the power 3 factorial 3 plus dot dot dot, right? This is the expansion of e raised to the power x. Now I am changing it to the matrix exponential e raised to the power a, right? Now it will become what? Identity plus a, this will be a matrix polynomial, a square divided by factorial 2 plus a raised to the power 3 divided by factorial 3 and so on, right? Now you are writing this, you can write it in this way, right? This is nothing but P inverse. I am writing it as an similar matrices, right, of A. So this A can be written as P into dA P inverse. Again, using the power of the matrix, you can write it P into dA square P inverse divided by factorial 2, right? And so on, right? Now, as a simple calculation, you can take P outside. And here you may write identity matrix plus dA plus d square by factorial 2 plus d raised to the power 3 factorial 3 plus dot dot dot, and this will be multiplied by P inverse. And when we look at this expansion, then this is the expansion of e raised to the power dA into P inverse. So when you want to find the exponential of this matrix A, then this is nothing but P times e raised to the power dA P inverse A, right? And to find the exponential of a diagonal matrix is very simple, right? So this is the way to find the exponential of the matrix, right? Now I am taking some example, right? MCQ question depends on this discussion. Right here, let us see. Suppose 2, 3, 5 are eigenvalues of A, and B is equivalent to A. That means B and A are similar matrix, where P is what? Invertible. Determinant of P is not equal to 0, that means non-singular, that is what? Invertible. Then eigenvalues of B are what? So see, it is saying that eigenvalues of A are given, right? And here it is asking what will be the eigenvalues of B, correct? And it is saying that A is equivalent to B. So both have same eigenvalues, correct? So definitely this will be your answer. Are you getting my point? Right? Of course, because similar matrices have same characteristic polynomial, so same characteristic values, you can say eigenvalues with multiplicity. Second question saying that if third order square matrix is diagonalizable, third order and diagonalizable is given, then number of independent eigenvector of A is what? I already told you that there should not be any shortage of eigenvector. That means if n is the order of square matrix, right, n by n matrix, then definitely, definitely you must have n eigenvector, n linearly independent eigenvector. So this is 3 order square matrix. So answer will be 3. You must have 3 linearly independent eigenvector. Right? Now, the last question of this is what? If second order square matrix, order of this square matrix is what? Second order, has eigenvalue vector. Eigenvectors are given, that is 2, 0. First eigenvector is 2, 0, and second eigenvector is 0, 1. And if you look at these eigenvector, then you can say that these eigenvectors are linearly independent, right? And corresponding to 2 order, right? Order of this square matrix is what? 2, 2 order square matrix, right? And you have 2 linearly and eigenvector. So what it's saying, it is saying that there is no shortage of eigenvector, right? So definitely this matrix will be diagonalizable, right? So these are the way to find the uh, you can say the application of diagonalization process. It is very simple, and when you are using you are handling the objective type question, this result going to be very helpful, right? And I hope you can understand this session, you can understand the concept, right? I hope you enjoyed. Thank you very much.